CD, we did terrace housing, all right? But for steel design, we are going to do some sort of industrial or commercial building. So in your group, you will go and try to source some architectural drawings for industrial or commercial buildings. And yeah, so you can start off with that first. Okay, you can start off with that first. Go look for get into your groups and go get the drawings first. Okay. And then for so that's group project. And then for the assignment, obviously the assignment is for timber design. So that's not going to start until June. So I just share with you the assignment first. You can take a look and then you can stay in the same group or you can go for a different group. So group project and assignment, all group work, but you can stay in the same group for both or you can go for different groups as well. Doesn't matter. Okay. All right. Okay. And the group project, in terms of marks, it has heavier marks. It's 15% for the group report and 10% for the presentation. So total 25%. So quite heavy, yeah. 1/4 of the entire course marks is for the group project. All right, and the assignment is only 5%. All right. So you know where to split your time, lah. Okay. All right. So for today, we will go through one more example. So hopefully for this example, we can be a little bit more extensive. Okay, I can cover more stuff. Right, before that, I need to open this table. All right, and I need to open this table. All right, okay. Okay, so let's go through one more example. Okay, so you go through this example with me so that you'll be better prepared for the exam, for the test. Okay, example. Now, this example slightly different from what we did last week. Okay, so simply supported. All right, simply supported. With a UDL and with a point load this time. All right. So the point load, let's say P. The UDL, let's say W. Okay. And then the span. Let's say the span is 4. Okay. Okay. Maybe let's say this is A, this is B. All right. So we have a 8-meter beam with a UDL of W and a point load of P in the middle. Yeah, that P is 4 meters from A and also 4 meters from B. So it's in the middle of the beam. Okay. Right. So for this one, I will tell you what P is. P is 50 kilonewtons. For W, you need to calculate. Okay. Okay. So P is 150 kilonewtons. Sorry, P is 50 kilonewtons. And then I give you GK. GK is 3. I give you QK. QK is 10. All right. And then you're gonna need to find W. For this W, you need to include self-weight of beam. Okay, so let's now let's finish the question first. Okay, we haven't finished the question. Okay, so in terms of loading, we have P equals to 50, but for W, I haven't given you W. You have to look for it. But you know that QK is 3 kilonewton per meter run. No, GK is 3 kilonewton per meter run. QK is 10 kilonewton per meter run. You need to find W, which is GK plus QK plus SW, self-weight of the beam. Okay, that's for W. Okay, now the beam itself, beam is, let's say, 406. 178 UB berapa? 46178 UB74. Okay. S275. Okay, so beam is this 46178 UB74 S275. All right. So the first task is that everything? Oh, yeah. Beam is fully restrained. Yeah. Beam is fully restrained. Okay. Right. Okay. So your first task is sketch the shear force diagram and bending moment diagram. Okay, so let's do this together. Sketch the shear force diagram and bending moment diagram. If I use blue color, is it okay? No, blue color, like the lines in the background. Okay, you're red. Right. Okay. Sketch the shear force diagram and bending moment diagram. Now, before you can sketch the shear force diagram and bending moment diagram, you have to find W. So let's find W. Okay. Now, 406,178 UB74. Now, so we know P has been given 50, but W we don't know. Okay, but W, yeah, W we don't know, but W is 1.35 GK plus self-weight plus 1.5 QK. Okay, so SW is short form for self-weight. Yeah? Okay, SW is short form for self-weight. All right. So W is 1.35 GK plus self-weight plus 1.5 QK. Okay. Okay. So GK we know. Yeah. Yeah. What is GK? Tell me.
3 kilonewton.
Correct.
Damn it.
3. Yeah. Thank you. What is self weight?
In the table,
Yeah, it's in table. Correct. So you look at this beam. You look at the table. Now, so I last time I mentioned before. So if you look at the beam, 406. Okay, look at the beam. Look at this. 406 times 178 times 74. Okay, 406 is the approximate. So 406 is the approximate height of the beam. 178 is the approximate width of the beam. 74 is the approximate weight of the beam, self-weight of the beam. Okay, so actually it's there. It's 74, but but you cannot use that 74. Yeah, you cannot use that 74. Like what some say, you should go to the table because 406 is approximate. 178 also approximate. The 74 also approximate. You go look at the table. It's actually not quite 74. What does the table say? The Excel table? I can show you, but then I have to stop sharing this screen. Then I have to share the other screen. You learn how to use the table. Okay? You do this exercise with me as if you are doing the test. Then for the test, you will be able to score. Okay? You don't, otherwise, if you start learning how to use the table during the test, then habis finished. Okay? Try to look for the self-weight from the table. How much?
74.2.
74.2.
Yeah, correct. Yeah. So let's go the other side first. Correct. Yeah. So, okay, maybe I do this. Yeah. So self weight is 74.2. Correct. Unit?
Kilogram per meter.
Correct. Okay. Now, we have to do some conversion here. Yeah. Because why? VK is kilonewton per meter. QK is also kilonewton per meter. So kilogram per meter, we have to convert to kilonewton per meter. So 74.2 kilogram per meter. What is it in kilonewton per meter? Multiply by what? Kilogram to kilonewton. Multiply by what?
by gravity.
Yeah. How much?
0.981.
Okay. Good. Everyone, you follow us? Hey, 0.981 or 9.81? Double check. Yeah.
Nine point eight one.
9.8. But 9.81 gives you what? 9.81 gives you Newton, right?
Yeah.
Okay. All right. So 9.81. But 9.81 gives you Newton, I think. So let me get my calculator. All right. Hey, so what is it? 727.9 Newton per meter. Okay, but we want kilonewton. So what does that give us? So Newton, total Newton, it's zero. It's you move 3 decimal places. So you get 0.27. 8 lah, 8, 8, 8. It becomes 8. Okay, 0.728. Okay, yeah. Okay, so after the conversion, you get 0.728 kilonewton per meter run. So you put your now the unit is the same. Yeah, now it's also kilonewton per meter. So now you can put this in there. Okay, so 1.35 times 3 plus 0.728 plus 1.5 QK. QK is what? 10. 10. Okay, so this is your permanent load. This is your variable. Okay, so 1.35 times permanent plus 1.5 times variable. Okay, now permanent is your GK, but also your self weight. All right. Okay. So, calculate for me. What is the total? Good. 3 plus 8, 3 plus 0.728. 3 plus 0.728 is 3.728 times 1.35. So the first one is 5. This is 5.03. The other side is 1.5 times 10 is 15. So the total is about 20. Yeah, we make it 20 lah. Okay, 20. So the W is 20. All right, so now let's redraw it. Now let's redraw it on our beam. So you basically have a point load of 50 in the middle, W of 20, and it's 4 meters and 4 meters. All right. All right, so that's the loading. Now, we can do SFD now, shear force diagram. How do you do your shear force diagram? So shear force diagram, difficult to draw a straight line. There's a ruler kan? There used to be a ruler here. No more ruler. Don't want to use this. Okay, never mind. All right, okay. So SFD, Right, okay. So the way you start SFV, always start from the left-hand side. All right, you start drawing SFD from the left-hand side. Now, to start drawing from left-hand side, you need to know what the value on the left-hand side is. What do you think the value of the left-hand side is? It's the support lah. It's a support reaction. All right. So we go back to the loading, we find at A lah, A enough. What is the support reaction at A? What VA? Let's say VA. What is the support reaction at A? We call it VA.
210 kilonewton.
Yeah. How did you get that? So it's 50 divided by 2 plus 20 times the length, the total length, or you can do half the length. 20 times the length, and then divide by 2. I think it's like that. Yeah. Okay. So VA, so 210 is the total load. Yeah. 210 is the total load. So 20 times 8 is 160. 50 is the point load. Yeah. So 20 times 8, 160 plus 50, 210. That is the total. That is a total load on the beam. Okay. But the total load of the beam, half will go to A because the beam is evenly loaded. Everything is evenly loaded. Therefore, the 210, half will go to A, half will go to B. That's why you divide both by 2. Yeah. So it's 210 divided by 2, 105. Okay. So the support reaction at A is 105. So you go back to shear force diagram. You draw your 105 at A. Okay, you draw your that 105 is positive, huh? So you draw your positive 105 at A. Alright, you always start drawing from the left hand side. Okay, so A is positive 105. All right, okay, now what next? Now, so as you go towards the left, there's a UDL of 20 kilonewton per meter run pushing down. So every 1 meter you go to the left, you lose 20 kilonewton. So that means we drop. So every 1 meter, we lose 20. So 105 minus 20, how much? 85. You go another meter, you lose another 20. 65. So you keep going. You keep going to the center. You keep going to the center. What do you think that load in the center will be? When you get to the center, how many meters to the left will you travel? How many meters?
20 times 4.
4, correct. Yeah, 20 times 4, correct. So by the time you get to the center, you would have lost 20 times 4. You would have lost 80. So therefore, the shear force in the middle is 105 minus 80, minus the 20 times 4. Yeah. Yeah. So it's 25. So it's positive 25 once you get to the middle. Everyone follow so far? Okay? Everyone okay?
Okay, Doctor.
All right, okay. Okay. So once we get to the middle of the beam, it's 25. Now, at the middle of the beam, there's also a point load of 50. Yeah, in the middle of the beam, there's also a point load of 50. So pushing down. So from 25, we have to go down by 50. So where does that take us if we go down by 50? So from 25, we go down by 50, we end up here. How much? How much? 25 minus 50, how much?
Minus 25.
Yeah, minus 25. Okay. What happens after that? We continue. We still continue losing 20 kilonewton. Yeah. There's still 20 kilonewton. If we keep going left, we still keep losing 20 kilonewton. Yeah. So I go left by 1 meter, I still lose another 20. So negative 45. I go left again, I lose another 20 minus 65. I go left 1 more meter, I lose another 20 minus 85. And then up to the end, So this is 4 times 4 meters. So minus 8, so minus 105. Agree? Then what happens? Then at B, now this is a uniform distributed beam. Okay, so if VA is 105, VB is the same. Yeah, because it's uniformly loaded. So once you get to the end, then it's positive. You add another 150. 105. You get to 0. There. It's like this. That's your shear force diagram. Any questions? Can follow on? All right. So if you can follow, then that's a shear force diagram. Next, bending moment diagram. All right, bending moment diagram. Now, this is a simply supported beam. This is a simply supported beam. Simply supported beam means the bending moment diagram at A and B has to be 0. Yeah, simply supported. Meaning the moment at A and the moment at B has to be 0. So you only have to calculate the moment in the middle. Yeah. What is the moment in the middle? You go back to your shear force diagram. You go to your shear force diagram. The moment in the middle, Z. So I draw a straight line to join the shear force diagram. So I've drawn a straight line to join the middle of the shear force diagram with the middle of the bending moment diagram. Yeah, I draw a straight line down. Okay. Now, the moment in the middle, can you guess what it is? How do you calculate from the shear force diagram? So the bending moment in the middle of the beam, you can calculate from the shear force diagram. How do you calculate? Any idea? Anyone?
The reaction at support times half the distance, and
Yep.
they say what? The distributed load times half the distance square over 2.
You can do that. You can do that. But that is a little bit complicated. There's actually a faster way. It's the area. It's the area of the shear force diagram. So, meaning okay, maybe now I don't want to look for the middle. I want to look for moment here. I'm gonna use blue color. No, I'm gonna use green color. Let's say I want the moment here. Yeah, here, green. I draw a straight line up to the bending moment diagram. If I want a moment there, the moment is that area there. Very simple. You calculate the area, you get the moment there. It's basically the moment at whichever point is the area of the shear force diagram from A to that point. Yeah, like you say, you can also use lever arm, like use the reaction method. Yeah, you can use that method, but this method is faster, I think. You just calculate area, finish. Okay, so if you want the moment at the X, the green point there, you just calculate the area from A to that point. Then that's the moment, okay? But we want to look for the moment in the middle. So moment in the middle, what do you think it is? Moment in the middle means you calculate the area of the shear force diagram up to the middle. There. All the area. You calculate the area for me. You tell me what is the number. That will be the moment. What is the area? So that is trapezium. That is a trapezium. You can split it. You can split this 25. This is 25. And then this is what? It's 105 minus 25. So this is 80. Okay, it's not exactly to scale. Huh? It's not to scale. But yeah. Okay, so now, and then this length is 4 meters. Yeah, yeah. So area, simple. It's 25 times 4 plus 80 times 4 divided by 2. Yeah. You have a triangle and then you have a square. The square is 20 times. Yeah. Okay, this part how much? The square how much? 25 times 4. 100. The triangle how much? 80 times 4 divided by 2. 160. So the moment is 160 plus 100, the total area lah. I split it so that it's easier to calculate. Okay. But you have to add it back up. So you add it up. So 260. So the moment there is 260. And it should be parabola. Like that. Everyone follow?
Yes.
All right. Okay. Okay. So that, if you can do this, then you got half the question right already. Okay. So we have the shear force diagram, we have the bending moment diagram. So next, so A is done. So let's do B. Okay. So B, I will tell you to classify the section. So classify the section. First, you have to find the epsilon. Now you have to open your notes. Now you have to open your notes. Okay. Epsilon for grade 275 is what? You go to your notes, the section classification part. Epsilon for 275 is what?
0.92.
Yeah. Okay. Epsilon for grade 275 is 0.92. Okay. Next, So let's start classifying the section. So let's do the flange. So when you classify the section, you separate it between the flange and the web. Okay, you separate it flange and web. All right. So we do the flange first. For the flange, what is C? Now, again, you go to your section table. Yeah, I won't draw. You look at your section table. It will tell you what the C is. C is, I draw it here. C is this. C is this dimension there. Yeah, if you look at the section table, the section classification, there are two tables, one for flange, one for web. You look at one for flange. All right. So you need to open your Excel table. You have to find the total length of the flange. And then you have to minus the web, minus the root radius. Okay, what is the total width of this beam? This beam is 406, 178.74. You give me the width. What is the width? What is the B from the Excel table? Quick.
One 179.5.
Okay. 179.5. Thank you. Okay, so you can see now C, you C is the total width, divide by, you have to take away the web thickness. You have to take away 2 times the root radius, and then you have to divide by 2. Okay, to get C. You can do whichever way you want, but it's that length that you want. Okay. Let me write B first. Sorry, it's B. Yeah, it's B minus TW minus 2R divided by 2. Okay. So what 179.5, right? Just now. Okay. What is TW? What is TW from the table? Someone else. Ryan, what is TW? Ryan?
Doctor, I'm looking at the table right now.
Okay.
TW.
TW, web thickness.
Uh, 9.5.
9.5. What is R? Root radius.
Ten point two.
10.2. Okay. The whole thing divided by 2. Everyone agree, yeah? Is it correct? Did I get anything wrong?
Agree, doctor.
Agree, yeah? Okay. All right. Okay. So let's calculate this first. Let's calculate C. 179.5 minus 9.5 minus 10.2. 10.2 times 2 is what? 20.4 divided by 2. 74.8. What is TF? Flange thickness?
$16.
Ngam 16. 16.0.
Yes.
Okay. Therefore, to check the flange, you need to do C over TF. Therefore, it's 74.8 minus 16. So 74.8 minus, no, not minus, divide by 16. So you get 4.675. Okay. Now, so C divided by TF is 4.675. Now, if it's less than 9 epsilon, then it's class 1. Okay, if it's less than 9 epsilon, it's class 1. However, if it's more than 9 epsilon but less than 10, then it's class 2. Now, what is 9 epsilon? 9 epsilon, how much? It's 9 times 0.92. 8.28. Okay. So, do you think C divided by TF is less than 9 epsilon? I've calculated 9 epsilon there. It's 8.28. Is it more or is it less? Is C divided by TF more or less than 9 epsilon?
Less.
Yeah, less. It's 4.6 only. 9 epsilon is 8.28. All right. So it's less than 9 epsilon. Therefore, it's class 1. All right. Okay. Next, we do the wet. Similar. You find C. Now, for the wet, you have the root radius. Come down. It's this. That's a C. All right. So the C for wet is, you can use your formula, but I will do the top half and then and then multiply by 2. Okay. So the wet is the height minus 2 times the flange thickness plus the root radius. Like this. Yeah. Why? Because you have one root radius there. You have one TF there. You also have one root radius there. You also have one TF there. Yeah. So you basically add TF plus R times 2. Then the whole thing minus H times 2. Yeah, then the whole thing minus H, you should get C. Okay. So what is H? Someone else? What is H? Quickly. The quicker we do it, the quicker we can finish the class. H from the table is what? We know TF is 16. R is 10.2. We just need to know H. Give me H and then quick.
412.8.
412.8. Okay. All right. Thank you. So 16 plus 10.2 times 2 minus 412.8. 360. 4 millimeter. Now, TW, we had it just now. TW 9.5. Yeah, 9.5. Okay. So therefore, to check the web, the formula is C divided by TW. C is 360.4. TW is 9.5. 37. .94. All right. So 37.94 is the ratio. Now, what is the limit for class 1? The limit, so now we go to the next table, the limit for class 72 epsilon. Okay, so for class 1, the limit is 72 epsilon. What is 72 epsilon? 2 times 0.92. 66.24. Now, C divided by TW is 37.94. 72 epsilon is 66.24. So obviously it's less. So this is less than 72 epsilon. So therefore it's class 1. So therefore the flanges that two and web are both class 1. All right. So finish part 2, finish. Okay. Okay, C. C is verify. If the end support of the beam is adequate for shear. All right. So basically, it wants you to check the end of the beam. Is it okay to support the shear force or not? So shear at the end of the beam. So it's this formula. So you go back to my notes. It's this formula: V ED divided by VR DC has to be less than or equals to 1. If it's less than or equals to 1, then then it passes. If it's more than 1, then it fails. The beam fails. Okay. So if less than or equals to 1, beam it's okay for shear. It passes. If it's more than 1, then the beam fails in shear. Okay. If it's less than or equals to 1, it's okay for shear. If it's more than 1, then it fails in shear. So you do this check. Now, this check, now, end support of the beam. Now, that means the VED is from your shear force diagram. It's the 105. Yeah, 105. and support 105. Very simple. It's the 105 kilonewton from SFD. All right, so VED is the 105 kilonewton from your shear force diagram. The only thing you need to calculate is VRDC. This is the only thing you have to calculate, VRDC. All right. So, what is the formula for VRDC? It's AV times Fy divided by square root 3 divided by gamma m naught. All right. You look through your notes. That's VRDC. Hey, did I ever share this slot with you guys? Let me see. Yeah, I shared before. Oh, no. Beam design, I haven't shared, right? Yeah. No, beam design, I haven't shared. So the shear and the moment formula, I haven't shared with you. I will share later. All right, but but it's basically this this formula. Okay, BRDC is this formula. So Fy, 275 square root 3, gamma m naught is always 1. The only thing you have to look for is AV. So look for AV. Now the formula for AV is okay, like this. Let's take a quick break here. All right, let's take a quick break here. While I PDF my notes, and then I will share my notes to you. Okay, then you can refer your notes while we go through the example. Okay. While we are having a break, I will show you the attendance so you can do the attendance. The slot and slot show QR. All right. All right. Did you get the stuff I shared on WhatsApp? Okay. Ada? Okay. Right. Okay. So let's continue. Right. Okay. So you open up the PDF file that I shared with you, the beam design one. Now that PDF file is incomplete, which is why I didn't share with you earlier, because there are still more stuff that I need to add after it. But it's for the other topics lah. It's for the other topics. For this test, there's enough information there for you. Okay, so I share it for now, just for your information. Okay, but obviously there will be a newer version of this PDF file in the future. All right. Okay, right. Okay, so you open up that file, the beam design PDF file. You double check the formula for VRDC. Is it correct? You look for the shear design part. Correct, right?
Yes, correct.
Yeah, okay, good. Thank you. Now, can you give me the formula for AV? So VRDC is AV times Fy divided by square root 3 divided by sig gamma m naught. Okay? Fy 275. Gamma m naught is 1. The only thing we don't know is AV. What is AV? So AV is also given on the same page. Now, you want the AV for rolled I section. So what is the formula for AV for a rolled I section? It's A minus what? A minus what?
2B TF plus TW plus 2R times with TF.
So A minus 2B times TF plus what?
Plus TW plus 2R times with TF.
The whole thing times TF.
Yeah.
Like that, correct?
Correct.
Correct, yeah? Okay. So what is A? So A, you need to open up the Excel table. You go to the Excel table, it's the very last column.
$94.5.
94.5. Now, the unit is, be careful. So you have to be a little bit careful here. 94.5, but the unit is cm squared, whereas everything else is mm. Okay, so we have to convert that 94.5 later, right? But we do that later. So minus 2b. B, we have it from the classification just now. B from the classification 179.5. Yeah. 179.5. TF, we also have it from the classification TF 16. Okay. Plus TW 9.5 plus 2 times R is 10.2. I can't just remember that. And the TF is 16. There. That's the formula for AV. So 94.5 is in cm squared. We have to convert to mm squared. $94.5 to mm squared is times 10 to the power 2. Okay? To bring it to mm squared. Okay. Minus 179.5 times 16 times 2. 5,744 minus 20.4 plus 10.5 16 4 plus 478.4. So the total is 1 2. So 9450 minus 5 744 plus 478.4. So 9450 minus 5744 plus 478.4. So should be AV should be 4184.4 m squared. So substitute this back in AV. We get VRDC is equals to 4184.4 times 275 divided by square root 3, the whole thing divided by 1. Okay, so 275, okay, divided by square root 3 brings us to 6, and then the whole thing divided by 1 brings us to 6, 4, 3, 6, 2.73 Newton, which is 664.36 kilonewton. Okay, 664.36 kilonewton is our VRDC. So therefore, we throw this back into the main formula there, VED. This is the check that we have to do, VED divided by VRDC. Okay, so VED, I told you, VED is the 105 from your shear force diagram. VRDC, we just calculated 664.36. Find the ratio. Zero 0.158. 0.158 is less than 1. Therefore, shear check pass. So it's okay. So the beam is okay for shear check pass. Any questions for this part? Any questions for this part? Anyone?
For me, clear.
For you clear? Okay, thank you, Sam. What about others?
Clear.
Okay. Give me a second. I need to ask a question. Someone else. Yeah. All right. Okay. All right. So no questions on shear. We move on to the final part. The verify. How did I ask verify? Okay. If, how come? So verify if the mid span moment wait. Verify if the midspan of the beam is adequate to resist the moment. Okay, so basically now we're doing moment checks. So we've done the shear check. Next, we do moment check. Okay, now moment straightforward. You go back to your moment straightforward. You go back to your beam. You go back to your beam design PowerPoint, right? The PDF file I've shared to you. There are 4 formulas there. Yeah, 3 or 4. 3 or 4. Yeah, so you go back to that PDF file I just shared with you for beam design. Page 8, fully restrained beams, moment resistance. There are 3 formulas there. The first formula is for class 1 and class 2. The second formula is for class 3. And the last formula is for class 4. Now, our beam is class 1 or class 2 or class 3 or class 4.
Class 1.
Yeah, class 1. So you use the first formula. So the first formula there is this. That's the formula. I should have used red. Wait. Okay, the formula is this. WPL times Fy divided by gamma m naught. All right, that's the formula. Very simple. Fy is 275. Gamma m naught is always 1. The only thing you have to look for is WPL. WPL, you go to the Excel table. You look for plastic modulus YY. What is plastic modulus YY? From the Excel table for this beam. Yeah. Quick. What is the plastic modulus YY for this beam?
1320.
1320. Unit cm cube. Kalau tidak salah. Yeah. So 1320 cm cube. Okay. Times Fy 275 divided by 1. So 1320 we have to convert to again to mm cube. 1320 cm cube we have to convert to mm cube. So times 10 to the power 3 times 10 times 275 divided by 1. So 1320 times 275, literally, basically. Yeah. Okay. So the answer is 363,000 times 10 to the power 3 Newton meter. No. Yeah. Newton millimeter. Okay. In our bending moment diagram, the unit is kilonewton meter. Yeah. In the bending moment diagram, the unit is kilonewton meter. So this moment, Newton millimeter, we have to convert to kilonewton meter. To convert it is times 10 to the power negative 6. So we end up with 363 only. Okay. Once you've converted to kilometer meter. So MCRD is 363. To do the check, it's MED divided by MCRD. Now, MED is from our bending moment diagram. This is from BMD. What is the moment from BMD? 19 something, right? What's the moment from BMD just now? The midspan. Quick. We're almost finished.
$260.
Oh, 290 kah? Satu lupa sudah. Oh ya, 260. Betul. Yeah. So 260 is the MED divided by MCRD 363. So you divide the two, is it less than 1? Yeah, 0.71. Well, 716, so 0.72 lah. 0.72. Less than 1. Therefore, moment check pass. Okay? If it's more than 1, then the moment check failed. Okay? But since less than 1, then moment check is pass. All right? Any questions about this, the moment part? Any questions? Okay, so if no questions, then that's it lah. That's it. That's basically finished. All right. Now, for the test, tomorrow no class, so no test because I have an event that I need to attend. Yeah. So tomorrow there's an event I need to attend. So there's no class and no test. I will let you know when the test is. It could be Wednesday afternoon. Okay, it could be on a Wednesday afternoon, but I will confirm with you later. All right. Okay, any questions?
No, okay, thank you, Doctor.
All right, okay. So no test tomorrow, huh? No test, no class tomorrow. All right. So I will let you know when the test is. Could be Wednesday, could be Thursday this week. All right. So I'll see everyone during the test.
Thank you, Doctor.
All right. Thank you.
Bye, doctor.